Okay, so it's a pleasure to introduce Nicholas Meadows. We'll be talking about higher theories and monads, so you can start when you're ready. Nicholas?
Okay. My talk is called Higher Theories and Monads, and it's about the Monad-Theory Correspondence in infinity category theory. This is joint work with Simon Henry. Our main theorem is the existence for a small, dense subcategory of a locally presentable infinity category. Our main result is an idempotent adjunction between what we call the A pre-theories and the infinity category of monads on E. So what we mean when we say this, we write, when we say the infinity category of monads, we mean in the sense that's defined by Lurie in higher algebra. And by the A pre-theories, we mean the infinity category of essentially surjective functors whose source is A. This adjunction identifies the concrete or the models for an A pre-theory with the algebras for the corresponding monad. And this could be seen as sort of like the idea that you have like this adjunction is also semantic preserving. And this is actually can be viewed as an analog of the main result of monads and theories by Bork and Garner for the infinity category case. Now, this is not a generalization per se, because they talk about enriched categories. They do a monad theory correspondence for enriched in the enriched setting. And we actually don't do this for enriched infinity categories. We do this for ordinary infinity categories. So we call the images following the terminology of this paper by Bork and Garner, the images, the respective functors, the A theories, and the A nervous monads. We say that a monad with underlying endofunctor M is a monad with arities if the underlying endofunctor post-composed with the restricted unata embedding preserves the presentation of each object as a colimit and E as a colimit of objects in A. And here, because we're now talking about our results as opposed to the Bork and Garner results. So presheaves here stands for simplicial presheaves. And similarly, we also, similarly to Bork and Garner, obtain a characterization of the essential image of the functor mu as monads with arities. In other words, the A nervous monads can be identified with the monads with arities. So what are some applications of this result? The first application is the structural theorems about monads. So Lurie defines the monads on an infinity category in terms of the formalism of left modules over planar infinity operad. So proving general theorems, structural theorems about categorical constructions like colimits, etc., is not easy. But the nerve theorem guarantees an adequate supply of nervous monads, which permits us to prove various structural theorems in the context of A pre-theories and their models. And an example of this is a local presentability result for the algebras of a monad over a monad, and this sort of generalizes some results from Lurie and recovers some, and I guess gives an infinity categorical analog of some classical theorems. The other idea is the idea of infinity categorical extensions of classical monads. So by exploiting this adjunction, we explain how certain infinity categorical monads can be viewed as extensions of classical monads. And this actually suggests a general procedure to construct an infinity categorical counterpart of a one or two categorical structure. The final application is that we can partially recover the results in a paper of Chu and Hogsang, where they talk about a special case of the nerve theorem relating to Cartesian parametric right adjoint monads. And we can sort of partially recapture some of their results using our work, and we also can kind of interpret their results in our language. The thing is that these Cartesian parametric right adjoint monads are kind of they're a special case, so we can't, and they have special properties, so you can't recover all their theory just from this nerve theorem that we have. So I'm going to just for context, I'd like to explain a little bit about the Bork and Garner kind of result, or like some of the language that they use, and also a little bit about particularly I'd like to go to the concept of like explain what they their notion of a pre-theory, and I'm going to review some basic concept in categorical logic to do that, which many people are probably familiar with, but I feel like I need to kind of do this to just to have like a common background for the talk. So so a Lavoisier theory can be thought of as a category that describes a kind of mathematical structure, and they're simply defined as a category with finite coproducts in which each object is a coproduct of a single object. The particular examples of the structure are models of the theory or product preserving functors from the opposite category to set, and the category whose objects are free groups on n generators is a Lavoisier theory. And this is in particular the Lavoisier theory that describes groups. If we have a model, then the underlying set of the group is given by evaluating on the object F1, and the multiplicative structure is going to be induced by this this map between the group on 1 generator to the group on 2 generators, which maps the 1 generator to the product of the 2 generators. So on the other hand, if we have a group, we can define a model by taking HOM into that group, and these constructions are inverses of each other. And so you can see that the models of this Lavoisier theory can be identified with groups. Similarly, free associative K-algebras are the Lavoisier theory for associative K-algebras. The skeleton of the category of finite sets is the Lavoisier theory for sets, and other examples like related to Lie algebras abound. For instance, so the definition from Bork and Garner paper is that if I have a locally presentable category E and a small dense subcategory A, then an A pre-theory is a bijective on objects functor A to F. And the concrete models are the objects are defined as the category given by this pullback. If we let, for instance, if we take E to be sets, A to be finite sets, and F to be a Lavoisier theory, then the concrete models are just going to be models of the Lavoisier theory in the usual sense. And Lavoisier theories capture finitary operations borne by sets, but we can also capture more general things using this definition. So for instance, if E is the category of directed multigraphs, A is the full subcategory on graphs that are just strings of length n, the pre-theories will capture structures in which we build vertices and arrows from paths of arrows. So we get things like categories with involution, groupoids. And we can construct a pre-theory whose models are categories, and we start with A, these category of graphs. We add composition and unit maps, as well as certain morphisms. And then we add 15 equations, such as the one expressing associativity, and we get something whose models are categories. Now, Bork and Garner worked in the V-enriched setting, or V is some symmetric monoidal category. And here the models would actually be basically V-enriched functors from whatever the category, from F to V enriched over itself. And but we're just focusing on the case of sets because that's just what our infinity categorical result generalized, or sorry, the unenriched setting, because that's what our infinity categorical result generalizes. So to go further, we need to describe the infinity category of monads on a given infinity category E. But before this, we need to explain the concepts of monoidal infinity category, left action by a monoidal infinity category, and left module objects. So a monoidal infinity category is a co-Cartesian fibration, so that the induced satisfies a certain property. We can think of the induced maps of fibers as encoding the multiplication, the units, as well as other things such as well as other higher coherences. So a particular example of this is if I have a simplicial monoid and if I have a quasi-category equipped with the structure of a simplicial monoid, and this would be the same thing as a functor from delta op to simplicial sets that satisfies some certain Siegel conditions up to isomorphism. And this will determine if I apply the nerve functor, the homotopy coherent nerve functor, then I get a functor of infinity categories to the infinity category of infinity categories, which by straightening yields a certain monoidal infinity category, which we can think of having a strict monoidal structure. And as an example, and this is the example that we use a lot of, if C is an infinity category, then the internal Hom from C to itself, which we denote NC, has the structure of is also a infinity category, and it has the structure of a simplicial monoid. And we can multiply, and the multiplicative structure is given by the following formula. This simplicial monoid structure is given by the following formula. So by the preceding example, then NC has a structure of a strict monoidal infinity category. An action of a monoidal infinity category on an infinity category C is encoded by a certain co-Cartesian fibration to n delta op times delta 1. And we have whose fibers at certain points are identified with C and M. And the action map is induced by a certain map of fibers. It is given by the induced map of certain fibers from the co-Cartesian structure. And as an example of such a thing, if I have a simplicial monoid acting on an infinity category X, then this gives a strict left action by a strict monoidal infinity category. And this is just by this sort of the straightening construction that I mentioned before. An inert edge of the nerve of the ordinal number category corresponds to an interval inclusion. And similarly, we have a notion of inert edges of n delta op times delta 1, which we use to define the notion of inert edges of M and C, which are co-Cartesian edges whose image under the structure map are inert. And this allows us to define the notion of monoid objects in a monoidal infinity category. And this is just a section of the structure map that takes inert edges to inert edges. Similarly, we have the notion, and in particular case of this is a monad. how Lurie defines monads, which are monoid objects for the strict monoidal infinity category and E. And we write MNDE for the infinity category of monads. And when I talk about the category the morphisms, it's just the full subcategory of I guess sections of n delta op times delta 1 on such objects. We similarly have the notion of a left module object, which informally is going to be an action of a monoid object of M on an object C, and that's essentially what a left module object is. And a left module object for the action of end E on E, whose underlying monoid is T, is called a T algebra. And we write e to the T for the category of T algebras. And so the action of end E on E in simplicial degree 0 is the obvious thing. It's just applying an endomorphism to an object of E, an endomorphism of E to an object of E. So there's the notion of monadic functors, which are equivalent to, which is just any functor that's equivalent to the forgetful functor, which takes a T algebra to its underlying object. And the Barbach-Lurie theorem characterizes these things as similarly to the classical Barbach theorem. And we write mon E for this full subcategory on monadic functors. The full subcategory of the slice category, sorry. So we have an equivalence of infinity categories between monadic functors and monads on E, and the opposite category of monads on E, which informally takes each monad T to its category of T algebras. And this theorem was alluded to in higher algebra, remark 4.7.3.8, but was not proven. We went to quite a bit of trouble to try to prove this in our preprint, Higher Theories and Monads. And to give you a little bit of an idea of how this monadicity theorem works, as well as how this theorem might be proven, I'd like to mention a bit about how Lurie proves his monadicity theorem. So what he does is, if you're given an adjoint, is the proof of the monadicity theorem somehow proceeds along classical lines at first. If you have an adjoint pair, you want to factor the right adjoint through the category of T algebras, where T is some monad whose underlying functor is G composed of F. Because remember that in the infinity setting, there's basically an infinite number of coherences, so that doesn't really specify it fully. So we want to show that G prime is an equivalence if G satisfies the hypotheses of the Barbach-Lurie. And in the classical setting, you just construct G prime fairly easily. So the structural maps just come from the co-unit and the unit. And once again, however, in the infinity setting, you have to specify an infinite number of coherences. So Lurie instead constructs this this map G prime in terms of a universal property. And under the equivalence, the map G prime is identified with the endomorphism monad for the action of T on the infinity category of functors from D to E. And I should explain what endomorphism monad is. The endomorphism monad is a monad whose underlying action map is a so-called endomorphism object, which means that it's a terminal object of a certain category end E, G, which are just given by actions of monads on G. And the monad T prime, this endomorphism monad can actually be identified with the object that co-represents a certain functor here. So in other words, the inverse of the equivalence between the opposite of monadic functors and monads takes G to its endomorphism object. So in one direction, it takes it takes T to its T algebras. The other direction is to take it to this endomorphism object. And so now I'd like to go back, now that the terminology of how monads work in infinity categories is established, I'd like to go back to the idea to my main theorem, which is the idea of this idempotent adjunction of infinity categories. So the map TH is going to be a composite of, first of all, the Kleisli category functor, followed by precomposition, the inclusion of this category of arities, and then finally the functor that takes something in the slice category to its essential image. And this is all in the infinity setting, so it's more complicated to construct than classically. The Kleisli category functor is just the usual thing. You take the left adjoint of this forgetful functor of the category of algebras, and you look at the full subcategory of the category of algebras on the essential image of that left adjoint. And the functor mu is the composite of this models functor that we define on the next page, followed by this equivalence between the opposite category of monadic functors and monads. And the concrete models are defined in terms of a certain pullback. The PR stands for simplicial presheaves. The I star is the restricted uneta. And the right vertical map can be shown to be monadic. And under the equivalence between monads and monadic functors, the co-unit of the adjunction can be identified with a map induced by the epsilon prime, depicted here, and induced by restricted uneta. So you can functorially take a partial left adjoint of these monadic functors over E. The point here is that we're working over a fixed base E, otherwise this wouldn't really make sense. And this can be done by adapting an argument from higher topos theory of Lurie. And what this argument is there's this infinity category that Lurie defines of left adjoint functors between locally presentable infinity categories. And there's this infinity category of right adjoints between locally presentable infinity categories. And this equivalence that Lurie constructs takes, so this should say, and this infinity category takes each x on one morphisms by taking each one morphism to its right adjoint. So you just adapt that, you can adapt that argument to construct the Kleisli, to do the functoriality of the Kleisli category. You similarly can construct the unit of the adjunction and verify, and then you verify the co-unit unit identities, and you verify the idempotence, by checking that TH of the unit is an equivalence. And the thing is that there's an issue with partial uneta functoriality in defining this co-unit map. And first of all, you start with the free co-completion transformation, embedding the category of algebras EM into the presheaves, simplicial presheaves, and this is just defined in terms of the universal property of free co-completion, and it's done in, and that's how Lurie does that. And you get in, and what we do is we had some technical lemma that allowed us to get a induced natural transformation of partial adjoints. Now the thing is that when we want to show that this, now in our definition of this models here, or this pullback here, this right vertical map is given by precomposition essentially, And we want to show that on the level of infinity categories, that this is actually right adjoint to the free co-completion functor. And in infinity categories, because you have an infinite number of levels of morphisms, this actually is not trivial, but this was essentially shown in this paper called Orthofibrations and Monoidal Adjunctions by Hebestreit, Linskens, and Newton. And then finally, you use an argument involving coens to get an induced natural transformation of partial of the thing that you want from this natural transformation of partial adjoints found in step 1. And that was kind of a big step in doing this proof. So now I'd like to recall that the nerve theorem. The nerve theorem characterizes the fixed points of an adjunction, of the adjunction that we construct between monads and pre-theories, and the a-nervous and the fixed point of the adjunctions are the a-nervous monads or monads with arities. And once again, this relates to a monad with arities is going to be something where the underlying endofunctor followed by the restricted uneta preserves this colimit presentation of objects in E as colimits of objects in the dense subcategory A. And a very useful fact about this result is that if I have a monad with arities A, then THM will give a theory whose concrete models are the same as M algebras. I wrote algebraic theory there, but I should just say theory, sorry. That's a typo. And this is just a consequence of the Monad-Theory adjunction. And also the description of the identification of M algebras and models. Yes, no, it's just a consequence of the construction of the adjunction, sorry. So we can use this. We can show that the category of all a-nervous monads has colimits, and that the inclusion of the full subcategory of a-nervous monads preserves colimits. And we have the following formula here. So how do we do this? So this is helpful because we can show that a lot of monads are actually going to be a-nervous in certain nice situations and for certain choices of A. And we'll get to that in a few slides. But the category of a-nervous monads can be identified with the full subcategory of this co-slice category on A theories. And so there's a bit of a typo here. It should be cat infinity A/, that's what that should read. And thus we can compute the colimits as colimits in this infinity category, this slice of the infinity category of infinity categories. And these are just identified with homotopy colimits in the model category presenting this. And in a model category, you're going to have all homotopy colimits, so that proves the existence. And then the latter equality is going to follow from the fact that these nervous monads are by definition the image of the left adjoint of this adjunction, and the fact that this left adjoint involves that pullback that I mentioned, defining the models, and the fact that the simplicial pre-sheaf functor is going to send colimits to limits. And when I talk about colimits, I'm talking about really what I'm talking about is in an infinity setting, I'm really talking about homotopic limits. Sorry, is there a question?
Yeah, I was just going to ask a question. Back on the previous slide. So are you using the terms A-nervous monads and monads with arities interchangeably?
Yes, I am.
Okay, just because in the classical setting, those are two different notions. Really, there's the Mark Weber notion, which is that of a monad with arities, and then his theorem essentially is that a monad with arities satisfies the nerve theorem. In other words, is A nervous, but they're two different things. So
okay. Well, I'm still okay. So sorry, I think actually, sorry. What I should say is I'm saying monads with arities are kind of like in the. I think of it as the. I'm defining it as the essential image of one of this functor. And then I'm saying the A nervous monads are these. Sorry, monads with Okay, so. So sorry. So maybe I have these terminologies mixed up. So monads with. But what I called A nervous monads are things that are in the image of this this functor.
So you mean the fixed points for the
fixed
adjunction?
Points.
So that's right. And then the monads with arities, can be captured using this sort of co-limit, can be described in more elementary terms using exactly a co-limit preservation condition. But yeah, so the nervous monads are the fixed points. And in the classical setting, at least, the monads with arities are a more restrictive class. Okay. But I don't want to confuse you on the terminology, but it might be worth having a look at for example, the Berger Melies Weber paper, Monads with Arities. Or we have a section about them in the paper with Richard where we show that there exist nervous monads which don't have arities, like the groupoid monad. But I think it's probably a terminology thing in this case, so I don't want to stop.
Yeah. So I just define monads with arities as the things that satisfy the nerve theorem, and then I said the A nervous monads are the fixed points of the adjunction, and that's how I guess.
Well, okay. Well, then they're the same thing. Then they're the same thing.
Well, we prove. Yeah. Well, we prove that the nerve. That's our version of the nerve theorem. Is that in the infinity setting is that these are the same thing. But yeah.
Okay. Thanks. Anyway, I'll just make that terminological remark, and leave it there.
Okay.
So,
yeah, I mean, I know that the Weber definition was a bit, or the Berger definition was a bit different than this. So,
yeah,
like I knew that. Okay, should I go next?
Yeah, go ahead. Go ahead. Thank you.
Okay. So, okay, good. So, a monad is said to be lambda accessible if the underlying infinity category is lambda accessible and the underlying functor preserves. I just want to make it 100% clear also that like we prove this, that like we prove that the fixed points of the adjunction are exactly these things that preserve this co-limit presentation, and that was one of the main theorems of our paper together. That's a point I'd like to make. Like in the infinity setting, I mean, not in the classical setting. Okay. Yeah. So, but anyway, a monad is said to be lambda accessible if the underlying infinity category is lambda accessible and the underlying monad preserves lambda filtered co-limits. So we actually showed that that as in the I believe this is also just an analog of something classical. A lambda accessible monad is C lambda nervous, for C lambda is the category of lambda compact objects in C. So colimits of lambda accessible monads exist. And if M is lambda nervous, then e to the M is locally presentable. And this is a corollary of this theorem 8 that we've talked about. So if we have a, and I'm going to say the proof of the corollary is this, if K is a pre-theory whose models are identified with the M algebras, then because the inclusion of this infinity category of right adjoint functors between locally presentable infinity categories in the larger infinity category of infinity categories is a right adjoint to the free co-completion, we can actually compute the pullback. This is also a, we can compute the pullback in PRR. And in particular, that means that the thing, this infinity category of models, which is equivalent to the category of algebras, is locally presentable. And this result about the fact that colimits of lambda accessible monads exist and that the category of algebras is locally presentable is a generalization, appears to be a generalization of what you can deduce from Lurie's higher algebra, because the main theorem about colimits of algebras over I guess algebras over monad, or rather more generally, I guess left modules over a left module objects for an action of a monoidal infinity category only really seems to suffice to prove that the category of algebras for a colimit preserving monad are locally presentable. So this is a refinement of that. And to sort of see how that, and this is 4.2.3.5 in higher algebra if you're interested. So finally, I'd like to talk about some examples related to symmetric infinity operads. So a symmetric infinity operad is going to be encoded by a fibration to the nerve of the category of pointed sets, pointed finite sets. And this is different from the planar formalism we used before to define monads, which is encoded by a fibration to the nerve of the opposite of the ordinal number category. And the fiber over the object 1, where you have a the distinguished point and one other object, is written as just O, and is called the underlying category. But it's, so we write alg O C for the morphisms of infinity operads, which means that you get basically a preservation of like a nerd edges, and a non-colored operad in our terminology is one whose underlying category is weakly contractible. Sorry, I should put that's a typo. It says isomorphic. It should be like homotopy equivalent. So if we have a non-colored operad and C is Cartesian closed, locally presentable symmetric monoidal infinity category, then there's a forgetful functor, which can be thought of as just taking the maps over the fibers over this one, and this is actually going to be a monadic. And this is just an application of the Barbeck-Lurie theorem. It's fairly straightforward. Recall that there's the E1 and E infinity operads, which model respectively homotopy coherently associative and homotopy coherently associative and commutative multiplication. There are an infinite number of intermediate EN operads, which express increasing degrees of commutativity up to homotopy. So if B is either set, groupoid, or spaces, and here we can think of groupoids as homotopy 1 types, just by the nerve theorem, and we let En be the En algebra operad, then the functor, as a consequence of our theorem on the preceding slide, this forgetful functor is going to be monadic from EN algebras in B to B. And the underlying endofunctor of the free algebra monad is just given by taking a certain free EN algebra functor followed by this forgetful functor. And this free algebra monad is actually nervous for the category of arities of finite sets, the arities being the finite sets. And this is an application of this nerve theorem that we mentioned. So if B is either set or groupoids, and the free algebra functor sends elements of B to elements with underlying object in B, then we can find a pre-theory whose I guess space-valued models and B-valued models respectively get identified with EN algebras in S and EN algebras in B. So we can think of that should be, there's a typo that says E1, it should say EN. We can think of this, if that's the case, then we can think of this free algebra functor from spaces as an extension of the free algebra functor for I guess for EN algebras. Sorry, we can think of the free algebra functor for EN algebras in S as an extension of the free algebra functor for EN algebras in B, since the former sends B to a free algebra with underlying object in B. And because these are both fin nervous monads, the EN algebras in B and S can be viewed respectively as the space-valued models for the identical pre-theories, which are given by these, which come from the following identical composites. Now, if we get that B is set, the E1 operad, and we take the E1 operad, the hypothesis of the theorem applies, and we can just verify this by using the explicit model for the explicit description of the free E1 algebra functor. And using a rectification result of Lurie, we can identify this forgetful functor from E1 algebras in set to set with just the usual forgetful functor from monoids to set. And what this means in particular is that if we look at K, the one categorical law, the Lawvier theory for monoids in the classical sense, then we get that the space-valued models and our sense we've defined of this gets identified with E1 algebras in spaces. And we can also think of this as saying that the free monoid monad is extended by the free E1 space monad. So because if I take B as either spaces or B is either sets or groupoids or spaces, to be honest, it's Cartesian. So you can identify it's which means in particular that and when I say that, I mean like the monoidal structure is given by a Cartesian product. That's what I mean by that. It should say B O times. We can identify E1 algebras in B with monoid objects in B. And also there's this fact that for some kind of operatic tensor product, EN algebras can be viewed, or EN can be viewed as an n-fold tensor product of E1 with itself. A tensor product of n copies of E1. So we get this first equivalence in the string of equivalences here. So we can apply actually a variant to the Ekman-Hilton argument to show that the objects of the E2 algebras in groupoid are braided monoidal groupoids. And you can similarly show that the E infinity algebras in groupoids can be identified with the two category of symmetric monoidal groupoids. And applying the theorem that I mentioned above for n equals to infinity and B is groupoid, we can see that the free braided monoidal groupoid monad and the free symmetric monoidal groupoid monad are extended by the free E2 and E infinity space monads. And it should be noted that for n greater than 2, similar examples are obstructed by the Bayes-Dolan stabilization hypothesis. So we'd need at least some kind of an n category to get En algebras. And for other reasons, I think this is impossible for n greater than 2. But so you need at least an n categorical theory to get something whose algebras are or whose models are going to be these En algebras by the Bayes-Dolan stabilization hypothesis. And this finally suggests a method by which I can give a infinity categorical extension of a one categorical construction of a one categorical this suggests a method by which I can give a infinity categorical analog of some one categorical structure in a relatively automatic manner. So if I have a dense one category in some infinity category E, and I have a monad on that one category, which is A nervous, then by applying the infinity categorical monad theory adjunction to THM, I would get a monad M prime on E that in some sense would extend M. And if I want to define the infinity categorical counterpart of a classical structure where its infinity categorical counterpart is not known, then this would be done by viewing the infinity categorical counterpart of my classical structure as the algebras for this new monad M prime I construct. So finally, I'd like to say a little bit about categorical patterns, which was this Chu and Hogsang result. So if I have an infinity category equipped with a factorization system, as well as a full subcategory of elementary objects, then they define the Siegel objects, which are essentially given by the following pullback, which means they're essentially the models in our sense for the pre-theory given by the inclusion of the right part of the factorization system into the inert part of the factorization system. And Chu and Hogsang characterize we characterize when this is going to be a big O in theory in our sense as coming from what are called extendable algebraic patterns. I'm not going to say what the condition of being extendable is, but the interesting thing about it is that the Cartesian parametric right adjoint monads are precisely those which arise from extendable algebraic patterns via our monad theory correspondence. And this is the main result of Chu and Hogsang expressed in, I guess, our terms. There are a number of examples of algebraic patterns, such as those. So for instance, there's one that comes from the usual inert active factorization system on Siegel's category. And in this case, this algebraic pattern is extendable. And the associated monad is the free gamma space monad or E infinity space monad. And you similarly have a algebraic pattern whose associated monad is the free n-fold Siegel space monad. And there are many other examples. There's a free theta n space monad on the category of globular spaces. and so on and so forth. There are many examples that fit into their formalism. But that's pretty much all I wanted to say. Was just, I guess that's the end of my presentation.
I'm okay. Thanks very much. We can have a round of applause for that. And yeah, if anyone has any questions, either here or online, feel free to go ahead and ask. Maybe I can ask one question. Well, first, thanks for the applications. It look very nice. I have just one question about something in our paper with Richard Garner, one result we had, and whether you have an analog of it, or whether you looked at it. So that's the nervous monads, as you showed, I think are co-complete, so they have co-limits. And one thing we showed was that they're exactly the co-limits of the free monads on signatures, or equivalently, the category of nervous monads is itself monadic over signatures. In other words, showing that the nervous monads are exactly the things presentable by free monads on signatures. And that was sort of at the end of our paper, and I wondered whether you looked at all at that result, or whether you could get an analog of it in the infinity context.
So I'm not familiar with the category of signatures. So can you tell me a bit about the category of signatures?
Yeah. Well, it's just so okay. So if you have A is your dense full subcategory of E, right? The category of arities, then the category of signatures is just, so a signature is just a functor from the set of objects of A to E. And that's then the category of signatures is just those. But so that's the category of signatures. So for example, in the classical set case, so if your arities are just finite sets, or the natural numbers, then a signature just picks out for each natural number a set of operations of that arity. And then you get that in that case, all the finitary monads are actually monadic over these signatures, or you can write every finitary monad as a co-limit of frees on these signatures. But maybe you haven't looked at that one, but it might just be.
It sounds like it would be something that would be interesting to do and useful, but we didn't do an analog of that theorem. So I don't have much to add to that, but other than that, I think that it would be like probably very useful if somebody did do that.
It might be interesting because it's really related to presenting structures based on simpler ones and stuff like that. So I can imagine it's useful for describing structures via presentations in the infinity setting, but that's why I just thought I'd mention it, because nobody ever looks at that theorem, I think, which is just at the end of our paper. So I thought I'd mention it in case you were looking at it, or you were interested.
Yeah, it kind of reminds me of something I saw from Hogg saying. Okay. But which seems like, because they had some kind of interesting, because I guess we mentioned something about how like there's this free operad, or this free algebra monad for an infinity operad, and it somehow seems like and then he had well, it felt like what he said in his theorem sounded almost like how would that be in your result be interpreted for like a in the particular case of an infinity opera, of the algebras for an infinity operad or something like that. I don't know. So I think it could be very useful. Thanks for pointing that out. But unfortunately, because I'm now hearing about this now,
yeah.
or I mean, I read the paper, but I mean, I didn't remember that part. Yeah. So it might actually be very useful, and it might give some kind of nice but it seems like it's related to this kind of structural theorem about algebras for operands that I saw in this paper Pog saying recently. So it's very interesting.
Yeah. Any more comments or questions? Well, if not, then let's thank Nicholas again. Okay.
Thank you very much for inviting me.
Yeah, no, thanks. It's a pleasure. Very nice talk. And so that's it for today, I guess, so we can stop recording.
Yeah.